This video is to show you how to do goal 1 in the energy unit. If we take a look at the first question, they're asking what happens if mass goes up. So we have to look at each of the equations because the first one, potential energy, which is m times g times h, they want to know what happens if m goes up. So what the best thing to do is to compare it. If you put ones in for each value, and think about the answer. You know the answer for potential energy would be 1. So what if your m goes up? So we're thinking, all right, rather than 1, make it something bigger, make it 2. But they're not telling you to change anything else, so you're going to keep the other values as 1. So you end up getting a 2 as your answer. So how would you answer that? If m goes up, like it did here, 1 to 2, then our potential energy went up from 1 to 2. So we would say potential energy will go up. If we look at the next question, what about kinetic energy? So kinetic energy has this half in it, which makes it a little more complex, but not too much. So if kinetic energy, if m goes up in this case, let's start with the standard where everything is valued at 1. So 1/2 times 1 is a half, times 1 squared is still a half. You get a half as the answer for that. So what if m goes up? So rather than 1, let's make it 2. Everything else stays the same. So 1/2 times 2 is 1 times 1, we get an answer of 1. So when our mass went up in this equation, our kinetic energy also went up because it started at a half and it ended up at 1. So kinetic energy will go up. So for the other two, if we think about h, if h goes up, it's going to be the same kind of reasoning. Think of compare everything back to the ones example. So rather than increasing our mass or g, make your height get bigger. You still get an answer of 2. So anytime any of these increase, your potential energy is going to go up. But if we look at the question for height and kinetic energy, there is no height in the equation. So we're going to say the kinetic energy will stay the same because they're not related in this case, unless they give you more information. But there's no height here, so we can say kinetic energy stays the same. How about V? What if V goes down? So now there's no V in potential energy equations. So we're going to say the potential energy will stay the same because there's no direct connection. But if we look at the kinetic energy equation, there is V in it. So if we keep everything else the same, keep it as ones or keep the half in there, but now we make the V smaller, if we put something like a half in there, 1/2 squared is 1/4 times a half is 1/8. So you're going to go to 1/8. So compare to our starting position where our original, if everything was ones, our answer was a half. If we make our V smaller, then we went down to 1/8. So we would say if V goes down, kinetic energy will also go down. So in conclusion, for this section, to change potential energy, what are the things you can change? Only m, g, or h. M, g, and h. To change kinetic energy, the only things that are going to change that are m and v. So m and v. Now for the second part of the problem, we're just going to compare or think about what's really happening when you change potential to kinetic, or when you change energy and you have a roller coaster go through the hills. So what you first want to do is think, all right, at the top, my roller coaster is going to be at rest. This is before it starts. So at the top, there's no kinetic energy. Because think of the equation, 1/2 mv squared. If you have no speed, you have no kinetic energy. So at the top, the roller coaster's at rest, kinetic energy is 0. So all of the energy is potential. Remember, potential is m times g times h. So if you have height, then you have potential energy. So all of the energy is potential. So let's just make up a number for this because it's going to be easier to think in numbers. Let's say you have 100 joules of energy at the top. So then we've learned to add those up. When you add them up, you get total energy. So the total energy is 100 joules at the top. One of the things you should learn from this unit is there's something called conservation of energy. And what that means is that anywhere the roller coaster is, energy is conserved. You don't just lose potential. If you lose potential, then you have to gain some other type. You would gain kinetic. So that total energy is going to stay the same. So let's consider the bottom part right here. Down here at the bottom, we're going to say there's zero height. And if there's zero height, then you have zero potential energy. So we're going to say at the bottom, what we have is potential energy is zero. So what has to have happened, according to the conservation of energy, is all of that energy has been switched over to kinetic. And so you'd have 100 joules of kinetic. The total energy has to stay the same everywhere. So it's 100 joules. So now let's consider question 6. As the roller coaster moves from position B, down here at the bottom, to C, what happens to the kinetic energy? So we're going to assume that there's another transition. So here you have some height. So at the top of C, that roller coaster would have potential energy again. So we're going to have to, where does it come from? It has to be lost from kinetic. So at the bottom, we'll have the most kinetic. At the top of this hill, it will have lost some, so it gets transferred over to potential. So we're going to say the kinetic energy decreases as it goes from B to C. The other way to think of it is, hey, kinetic energy is 1/2 mv squared. And just logically, what happens when if you're just coasting and you're going up a hill, you're going to slow down because your V is going down. This is just something that can be very intuitive to where you can understand that way also. So, question 7, in which position would the roller coaster have the most kinetic energy? That is going to be at the bottom, either at B or D. If it's frictionless, it's going to be the most kinetic at either place, because no energy will be lost to friction. If we do have friction, then it would be faster at B because some of the energy would get lost by D. But if it's frictionless, which is what we're assuming here, then B and D would be correct because it's all the potential is transferred over to kinetic. And lastly, using that total energy explanation, explain why these positions in question 7, B and D, must have the high kinetic energy. So we're just going to put this in words. We're going to say total energy is conserved. That means it stays the same. Total energy is conserved. So all of the potential energy at the top is going to change to kinetic energy at the bottom. And so therefore, if all of that energy is now kinetic, you're going to have the most down at the bottom than you would any other place.